Hello, everybody. Welcome to this webinar. My name's Chris Ryan, and I'm going to be talking to you today about PMP modeling with a couple of our tools, CatchmentSIM and Storm Injector. We've been doing quite a bit of work in this space over the last little while, and we've sort of built up the library of PMP methods we support and built up the integration between the products. And so I thought it'd just be a good opportunity to give you all a bit of a run through for a sample catchment of the different options we can do. So just for an overview of what I'm going to talk about today, I'm going to do a small example catchment of it's about 174 square kilometres on the Dungowan River. Probably take about 45 to 60 minutes. We'll see how we go, whether we have any time at the end to address comments or questions. There's a couple of people from CSS lurking around that may be able to answer some questions in the chat. I probably won't get to them because I've got a lot I want to cover, but anything that's left in there we'll review after the meeting and perhaps circulate some answers afterwards. So first of all, we're going to use CatchmentSIM. We're going to map the catchment and we're going to break up the catchment into sub areas. And then we're going to look at where this catchment sits in the context of the various PMP methods we have. We're going to use CatchmentSIM to generate the PMP method worksheet. And then we're going to go and apply two specific methods, the generalized short duration method for durations up to 6 hours and the GTSMR for the longer durations. And then we're going to export them to Storm Injector. In Storm Injector, we're going to use the new feature for extreme event IFD interpolations. We're going to import those PMPs and combine both methods into single data sets for the full range of durations. And then we're going to interpolate some IFD data for between the 1 in 2,000 year event and the PMP to enable you to process some of those extreme events with temporal patterns of your choice. We're going to look at both single pattern PMP and ensemble PMPs, and we're even going to do a little example of how you might do a 2025 climate change considerations adjustment if you wished, although I know that's obviously something you'd want to think carefully about before doing a PMP. And I guess that leads into this being just for demonstration purposes. I've made no attempt to calibrate any models, and I'm not familiar with this catchment particularly. So this is all just a software demonstration rather than any recommended engineering advice. I'll just put that disclaimer out there. So in general, what PMP methods do we have available to us? This is the image from the PMP documentation just showing the different PMP method zones. We have the GSDM, which covers all of Australia, but is only for short durations of up to 6 hours, and in some areas only 3 hours. And then depending on what part of Australia you're looking at, there are various longer duration methods, GTSMR and the GSAM being the main ones, and the ones that are supported by both Storm Injector and CatchmentSIM. The only ones that leaves out is the west coast of Tasmania method, which hasn't been implemented yet. The red dot here is about where our demo catchment is, right on the border with the GSAM transition zone. I'll show you that in the next slide. The catchment you can see here in the green polygon. You can see that as far as the GTSMR zones, it's right on the border. I think its catchment boundary sort of is actually the border between the GTSMR and the GSAM GTSMR transition zone. And it's in the 6 hour zone for the GSDM. Okay, just briefly on these methods, as I said, the GSDM is for all of Australia up to 6 hours. It's a single duration independent pattern that's a little bit front loaded with about more than 50% of the rainfall occurring in the first 40% of time. And that's the pattern there. The generalized Southeast Australia method, the GSAM method, It's for the lower parts of Australia. Has temporal patterns ranging from 100 to 40,000 square kilometres and durations ranging from 24 to 96 hours. It also has some pre-burst temporal patterns, which you can use to distribute pre-burst amounts of your choice across these patterns before you do the PMP modelling. And it also has single patterns and ensembles available too if you, the ensembles are based on historical storms. Similarly, for the GTSMR method, which stands for the Generalized Tropical Storm Method, we have inland and coastal zones, temporal patterns ranging from 100 to 150,000 square kilometres and durations from 24 to 120 hours. We've got single patterns, AVM patterns, as well as ensembles, historical ensembles, and other temporal patterns for Southwest WA. Now, I mentioned before GSDM method for the shorter durations is only a single pattern, but there's also some patterns out there in the literature, such as these from Jordan in 2005, where they developed ensembles of short duration extreme event temporal patterns, as well as a 7-hour pre-burst temporal pattern for distribution of pre-burst. So they're also available in Storm Injector, and we'll demonstrate how to use those today. So this is just an overview of the new extreme event IFD feature within Storm Injector. Now, this isn't a necessary part of modeling the PMF or PMP. This is only required if you want to determine IFD depths between the 1 in 2000 and the PMP and model those with various temporal patterns. And if you wish to do so, this tool will help you do it using the method documented in R&R Book 8, Chapter 3. It also allows you to interpolate durations. We mentioned before that GSDM tops out at 6 hours and the GTSMR a minimum of 24 hours. So if you want to do durations in between that, Storm Injector can interpolate those depths. And we also have resampled temporal patterns at 12-hour duration to allow you to do models for the 12-hour and sort of fill in that gap if you think that might be critical for your catchment. So if you do interpolate these extreme event IFDs, you can use them using the normal rare temporal patterns, or you can use PMP patterns or other custom temporal patterns that you may import into Storm Injector. As I said, this is not required for PMP, but it's often helpful and gives you that context of other events with very extremely rare exceedance probabilities. And then I mentioned before, we've got both single patterns and ensemble approaches, and we'll show both of those today. This is possibly a little bit technical for a demonstration, but maybe you're watching this on a recording and looking for help on how we craft these custom events in Storm Injector. So I'll just go through the naming convention very briefly. CSTM is the code for a custom event in Storm Injector, and the next field separated by these underscore delimiters is the custom temporal patterns that you wish to use, and they can be separated by that vertical line if you wish to use more than one set of custom temporal patterns. So in this case, we're using the GSDM, and that will apply for the shorter durations. And then we're using the 100 square kilometre GTSMR coastal AVM patterns as well. The next is the IFD header and suffix. So this is saying what column in the IFD locations we want to use for our rainfall. And if that data is in one of the rare rainfalls, we should put the suffix there too, so Storm Injector knows where to look. The next is the initial loss you want to use and the continuing loss. In these cases, they're set to the same as the 1% and the continuing loss from the data hub, subject to any overrides you might put in your settings tab. And then we have any rainfall depth adjustment we may use. So that's where a climate change adjustment might go, for example, and any continuing loss adjustment we may apply. If you want to use a custom ARF, you can specify it here. And then we put what we want to name our event there. So that's the basic structure. And it's worth keeping in mind that the settings you have will also come into play. So depending on what you want to do with pre-burst, we mentioned before that the GSAM approach, for example, has various pre-burst temporal patterns you can use. So you could adopt these and you can use custom amounts of pre-burst, or the GSAM coastal has its explicit amount of pre-burst, or you can use medium pre-burst from the data hub. All those options are available in the inject pre-burst into temporal pattern option, and they'll be used when you're applying these custom events as well. So it's just worth keeping that in mind. All right, so enough of the boring slides. I will bring up CatchmentSIM now. Okay. So this is pretty much a blank CatchmentSIM project. All I've done is put on a Google satellite in the area that I'm doing this model. And I've also got a little outlet here, just a location to remind me where I want to map this catchment. So the first step is to set up a blank DEM. DEM sort of forms the basis of all the calculations in Storm Injector. The resolution should be selected fairly carefully. You don't necessarily want to process that just based on the finest data that you have available, but you want to make sure all the calculations can be done in a reasonable amount of time. So to make things quick for this demo, I'm going to use 50 meters. Then we can assign the elevations in that DM based on some data I downloaded from Elvis. We just go assign DM elevations based on a raster DEM. Just going to use this data.tif file. This is just confirming the projection. And so now we have some basic terrain information in CatchmentSIM. So the next step is to hydrologic condition the DEM. So if we turn on the flats and pits at the moment, we can see that there's a bunch of pixels that are lower than their neighbors, which are going to cause problems from flow routing. So we have DEM and conditioning tab, and we can use the breaching algorithm just with the standard settings, process entire DM, and it will resolve all those pit pixels by breaching them. And if I refresh the display, I can now see that there's no pit pixels in the catchment of interest. And if I go to the flow mapping tab and hit map flow pass, I can sort of click on the screen and see where a droplet of water would flow. And that sort of shows that everything's working as it can. And we're in a position where we can now go ahead and map the catchment. To map the catchment, we would just draw an outlet. Again, I'll do it up here near this yellow one. And then we can hit map all to map the catchment. Basically, it's just determining all the cells where the flow point would go through that outlet, and then it maps the catchment. You can also do some stream generation. Say if I wanted to map streams with the 80 hectare contributing area and just show them for my catchment of interest, I set it up like that. And then we can now look to break up our catchment. If we just applied a PMP calculations here, we wouldn't be able to have any spatially varying rainfall. So to have spatially varying rainfall, we need sub areas. So on the subcatchment tabs, we can use breakup, and I can just select, just for this demo, I'll select 15 subcatchments of interest. And it's determining where the outlets will be. I can accept new outlets and refine the subcatchment. And that brings up the catchments, subcatchments there in red. They might be a bit hard to see. If I turn the DEM off, it might be a bit easier to see. You can see the nodal link arrangement in green there too. So that's the process of mapping the catchment and subcatchments, but I'm eager to get on to the PMP things, and they're done in the analysis tab. I open up the PMP field, and we've got 4 tabs. The first is for the method worksheet, and then we've got specific tabs for the GSDM, GTSMR, and GSAM. So to do the method worksheet, I'll just give it a name. I'm going. Our CatchmentSIM is distributed with layers for the zones and limits. So if we just hit add layer and open those. I just close my sorry about that. So now we can hit determine PMP zones and limits. You can see in the background that we've got these layers added to our project. And now we've done some zonal statistics to work out the methods that apply. You can see as far as the method goes, the vast majority of the catchment is in the GTSMR coastal zone. There's a small amount in the transition zone, but I think that's only because the border doesn't match quite perfectly. But I basically think that the boundary of this catchment is the boundary of the transition zone, and the entire catchment is in the 6-hour GSDM zone. And so you can see the specific methods have sort of been worked here. The GSAM methods are included, but as I said, they're only applicable to a very tiny part of the catchment. We can click Create Worksheet, and I'll just export something here. I'll call it, meet that person, call it PMP method. We export that. The Word doc should be opened up. And you can see this has come out of the documentation, but there's some text boxes that have been placed in it with the catchment name, the area, some of the flow chart yes and no's have been circled based on what it thinks is correct, and then the actual methods that are applicable have been mentioned down here. As I said, the GSAM probably wouldn't do, so you could delete them if you wanted to, and then when you're happy with it, you can print it to PDF or whatever you need. Okay, so that's the worksheet. So now let's go on to the GSDM method, which is the more complex of them. It has a range of things, and you can see already the sort of the familiar ellipses have been added to the background. But before I get to them, I'll just add a roughness grid with this terrain category grid. Now this almost always works out at being 100% rough. Just one of those things you have to go. And then we'll do the ellipsoids. If I can change the road, CatchmentSIM tries to work out the best angle for these ellipsoids to make sure that the catchment is contained in the smallest ellipse that's possible. So you can usually leave that rotation, but you can modify it if you need. And you hit reposition over display, and then you can sort of drag the mouse and you can sort of move this around and try and get the catchment contained and position the sort of the center ellipsoid, which will have the most intense rainfall as you judge best fit. Once you're happy with that, you hit finished. Then you can hit create and add vector layer, and you also notice that the grid layers option is checked in here. And what it's going to do now is populate vector and raster representations of those ellipsoids, and that allows us to do a bunch of zonal calculations and things like that, and that all feeds into the script that then comes up with these rainfall depths. You see these ellipses now. We can do some zonal analysis if we want, but we don't really need to do that. The export script will do it for us, but there is something worth noticing here is moisture adjustment factor. So the GSDM documentation has a map where you can pick out the moisture adjustment factor, but it can also be calculated by dividing the EPW annual grid by the seasonal maximization factor of 104.5. So we can do that here. We just need to make sure we have a grid, and we can get one of them from the GTSMR grids, for example. This EPW annual is the same in all the methods. If you just select it there, then you can see that it gets brought into CatchmentSIM, and we can add a math user parameter and calculate the average for the whole catchment. So you can see here that it's come up with an average moisture adjustment factor of 0.74. And I'll show you later that that matches pretty close to what's on the map. So now we've got all our required GSDM layers. Just tidy these up a little bit. Mostly the ellipses that we're interested in. And the next step is to go to the Export tab and run Macro Wizard, and we go to the PMP GSDM method. So this is a script that will calculate all the depths and populate the worksheet for the GSDM method. So let's run that. So I'll just call this GSDM. This is just setting the file path for the report. It's asking for a catchment name. And it's in New South Wales. Okay, and this is the duration limit. Now, the method worksheet told us that 6 hours was appropriate, and that's the default setting here, so I'll click OK. That's asking us for our roughness grid that we created earlier. Now, here we go. It's offering to use the catchment average math from the user parameter, which is reported there to a obscene number of decimal points, but it came up with about 0.74. So if I hit no, it'll bring up the map, and we can just see a catchment's about here. So about 0.74 is right. We're just trying to convince you that that method of calculating the map instead of having to pick it off the map is okay, but I'll enter it manually as 0.74. Now it's asking for our ellipses, and I'll pick those. Now it's offering to create rainfall depth grids and average user variables. I'm going to say yes. So you might notice on the left-hand side of the screen, it's now adding new grid layers for all the different durations in the GSDM method. And those grids will be populated with the actual rainfall depths for each ellipse. That allows us to create user parameters so that every subcatchment can have the rainfall depth for each duration reported. Now it's offering to export IFD location files for Storm Injector, which is, we definitely want to do this because that's how we're going to pass this information into Storm Injector. I'll hit yes, and then it's complete. So we can turn on these PMP zones, for example, and we can see the actual rainfall depths in each ellipse for each duration. If we go to the Manage Subcatchment Manager, we can see these user parameters at the end. We've got the moisture adjustment factors for each subcatchment, as well as all the PMP rainfall depths. And if we want to map those thematically, we can do that too. We just click on the subcatchment boundaries, apply thematic mapping, configure. We can say, okay, let's map based on PMP 6-hour depths, and we'll use this gradient, add all values. We do that. We can now see that we're mapping the rainfall for each subcatchment. And this is the information that we want. That'll be exported to Storm Injector in those rainfall files, and I'll just okay. So that's the GSDM. Now I'll just look at the GSTMR next. Go back to our PMP section and go to the GTSMR. Now this method has some grids that cover the whole country, so they're reasonably large. So we don't distribute them with Storm Injector by default, but you can click on this link here and download them. Now I will just copy where I've got these grids stored on my computer into that section, and then we can start adding these layers. So these are the attributes that we need for the GTSMR. So the first is the the grid of the topographic adjustment factors. The next is the decay amplitude factor. And we've already imported or created a grid for EPW annual because we use that to calculate the math for the GSDM. So that's already there. And I'll just add the EPW winter as well. Once we have all those grids, we can add the user parameters, and these create the actual subcatchment and catchment averages for all these parameters. And then we can also calculate the catchment averages here. So you can see these values, TAF of 1.14, DAF of 0.84, EPW annual and winter, and math annual and winter for these methods are all set up here. And once you've done this, then you can go to the next step of running the script. Again, to run the script, we go to the macro wizard, go to the PMP GSAM and run that script. And I'll just put it in the GTSMR folder, call it. It's asking us to select the GTSMR zone, which is the coastal summer zone. Again, a catchment name, state of New South Wales. And do we want to export the IFD locations to Storm Injector? Yes. Okay. Now, I forgot to show you the GSDM report, which I exported here. We just want to open that up. This is what you'll probably recognize from the documentation, but Storm Injector's created this for you. It's got the catchment details, roughness, the catchment's below 1,500 meters, so there's no elevation adjustment factor. The math that we entered, and then the PMP values for all durations and rounded to the nearest 10 millimeters. And then if you look at the individual durations, you've got all those values there. So these are for the catchment as a whole, but the values that are exported to Storm Injector are all for each subcatchment, so you get the spatial variation. So I actually put those in the wrong folder, but that's okay. And as far as the GTSMR we just did, you can see here the gauge files. They provide we open up one of those, you'll just see that they have the PMP depths for the GTSMR method here. From 24 hours to 120 hours, and the rainfall depths. And that's the information that goes into Storm Injector. There's also this summary file here that's produced in a similar way to the worksheet in the method document. And you can see that it sort of talks about the average TAF and DAF factors and the moisture adjustment factors and EPW values, and gives depths for each duration and preliminary PMP estimates for each duration. As far as spatial distribution of the GTSMR goes, that's based on how the subcatchment average TAF ratio to the catchment wide TAF varies. And you can see here that there's not a great deal of spatial distribution. So there's much more spatial distribution in that short duration approach. So that's something you're going to have to keep in mind. Those subcatchments that are closer to the central ellipsoid are going to have quite high GSDM 6-hour estimates. And you have to check they don't sort of exceed your 24-hour GTSMR. So they're things to keep in mind. But that's a summary document for the GTSMR. Okay. So we might go to CatchmentSIM next. Sorry, Storm Injector next. I'll just stop sharing for a second. All right, so this is Storm Injector. I haven't done anything in here. This is a blank project. So to do the extreme event interpolation and the PMP that we're going to approach, the first thing I'm going to do is import a WBNM model. Now we could have also exported this from CatchmentSIM based on our delineation, but here's one prepared earlier. It's now prompting us to determine the latitude and longitude so it can get the information from the data hub. I'll hit yes and convert these coordinates, which are in I know to be in MGA zone 56. And once I do that, we can see that the latitude and longitude of each sub-area is populated, as well as an area-weighted representation of the entire catchment lat long. And then we can hit the data hub button and we'll fetch all the data from the data hub, including point temporal patterns and so on. It's also worked out that we're in New South Wales and it's offering to apply the New South Wales jurisdictional advice. So I'll say yes to the continuing loss adjustment with a 0.4 factor and yes to using probability neutral losses. It's prompting us to use aerial temporal patterns. We're going to be using PMP analysis, so I'll just hit no because we don't need those. And normally, now the next step would be to get IFD data, but we're going to go a different way. But you can see all the metadata and things like that from the data hub are in there now. The reason we don't get IFD data here is because normally Storm Injector works with point rainfall data, but if you want to interpolate events between the 1 in 2000 and the PMP, you need to use aerial rainfall data. So I don't like to mix those, so we're going to leave that blank for the moment. If we go to the extreme event IFD setting, what we want to do is import all those data that came from CatchmentSIM. And you can see here is an example of that. So I've got GSDM as well as GTSMR data sets for each node. And you can see here that the latitude and longitudes match. And if we then group select all of them, Storm Injector will actually analyze them. It will realize that some of them are the same location and it will combine them. So once we do that, we can now see for example, this node that we have the GSDM results up to 6 hours, and then there's a gap, and then 24 hour to 120 are those GTSMR results. So it's automatically combined all those durations from different PMP methods into the same data set. So if we want to interpolate other events, we can look at them over in this table on the right. We should also notice that the area here has been calculated from the WBNM file at, again, 174 square kilometres, and it has been assigned an exceedance probability for the PMP of about 1 in 5,731,000. And that's from that figure I showed you in the presentation earlier, which comes from R&R, which basically just assigns a PMP exceedance probability based on catchment area. So given the PMPs are 1 in 5 million, we might want to add some more events here. So we could add a 1 in a million, for example, 1 in 1 million exceedance probability, and then it would just add that there and calculate the Z standard and other factors that it needs to do the interpolation. So once we're happy with that, the other thing probably I recommend at this stage is interpolate any missing durations that you're interested in. And that can be done by right-click here, interpolate duration. There's a variety of different methods. Linear is probably good in most cases. And just say we want to do the 12-hour. And now we can see that all these PMP locations will have a 12-hour rainfall depth as well. And you can see that that's where it is there. So another one you might wish to do is the 4.5 hour. For example, the Jordan temporal patterns, they have temporal patterns for 4.5 hours, which is not a standard duration come out of the GSDM method, but you could add that one too by right click here. Now the next step is to is to button 2, fetch bomb rainfall. And what that does is it goes off for every one of these locations with its latitude and longitude. It fetches the standard, rare, frequent IFD data from the Bureau and combines it all to interpolate these events. Now, since the Bureau has launched their new website, this has been a bit hit and miss. I find the bomb IFD data is not always working and it can be slow. So given that there's a lot of locations here, I'm not going to do that now. I'm going to load up a previously prepared project, which has got that data in there. We come back to here now. We can see now in this one, I interpolated the 12 hours, sorry, but I forgot to add an extreme event, but I can still add this later and put the 1 in a million here. Now what you see on the bottom part of the slide is all the point rainfalls for, if we pick a certain location, for example, you can see all the point data that's been downloaded from the Bureau for that, all the error reduction factors that are applicable for those exceedance probabilities and durations, all the aerial rainfall, which is just the ARFs times those point rainfalls, and there's a bunch of parameters that are required for the interpolation, and then the actual rainfall depths that are interpolated for these events for each duration, and all of it combined together as well. And you can see a graphical representation of that on the right-hand side. Once you're happy with that, you can hit button 3, and it will now go through every one of those PMP locations and copy it to the main storm generator tab, which will allow you to start using it in modeling. Okay, so that's complete. Next thing I should do here is just assign those IFD locations to sub areas. So basically each sub area now has its own IFD location. So node 8.01 has PMP location 8.01. So that's just showing you how the PMP rainfall is now fully spatially distributed over the catchment. Worth noting in the names of all these IFD locations that have been created here. So we have the rare events now have all the standard rare events, but they also have the 1 in 10,000, the 1 in 50,000, the 1 in 100,000, etc., all the way to the PMP, which has been renamed the 1 in 5,731,000 as per the exceedance probability calculated with it. And you can actually, if you go to the rare checkbox here, you'll see those as actual checkboxes that you can just tick and model them with the point temporal patterns if you want. So now we have our rainfall data in there for extreme events as well as the PMP. Now we can start looking at some custom events to model the PMP. So I'll just copy in some code for the first one into this custom event field. So this is just saying it's a custom event. We're going to use the GSDM and GTSMR coastal pattern. So this is a single pattern approach. This is the rainfall we're interested in, the 1 in 5,731,000 here, which is in the IFD location with the rare suffix. And then we have our assumptions around initial continuing loss, rainfall adjustments, and we're calling it the PMF in this case. So if I hit create storms, I get an error that says there is aerial #A rainfall IFD location selected, but the apply ARF checkbox is selected. This may cause a double ARF. So that's just telling us we shouldn't be reapplying the ARF if we're using rainfall that's already been aerially reduced. So I'll just uncheck that and go again. And now we can see the storms have been created. We've got 19 storms that it wants to run to model the single pattern PMF for all the GSDM durations and the GTSMR durations. And just worth noting here that there's actually two storms for the 12-hour duration. It's applying both resampled GSDM and a resampled GTSMR for the 12 hours. If you just wanted to do one or the other, you could right click and delete one. But by keeping both, it's like almost like a miniature ensemble. So if we click prepare model runs and just select the WPM file, we can run them. And now we can see the results. And maybe that's easiest to visualize with box plots. And we can see here the results. It's coming up with sort of a 4-hour critical duration, 5,500 sort of midpoint. We can view the hydrographs as well. See what that sort of 4-hour storm looks like. Okay, so the next example will be an ensemble-based approach. So I'll replace this with another custom code. And this one's using the Jordan extreme temporal patterns with the GTSMR coastal 100 temporal patterns, coastal historical 100. I should point out that these patterns are displayed here in the custom temporal pattern section. You can export this to CSV and have a look in them in detail. There's sort of over 4,000 PMP related patterns. You can see for these sort of historical versions, there's ensembles. So there's like 10 patterns for this 60,000 square kilometer temporal pattern, for example. So this will be an ensemble result. The rest is the same, and we're just calling it PMF ensemble. So if I hit create storms here, it's telling us that some durations couldn't be done, and there's a couple of frequent ones, and also the 4.5 hours. I mentioned that earlier. So if you wanted to be able to run the 4-hour Jordan temporal pattern, you need to interpolate that depth in that first sort of extreme event IFD step. But otherwise, it's produced 160 models it wants to run for this ensemble approach. I'm going to click prepare and add to the existing list so I can compare to the previous results. I'll get them running. Hopefully it won't take too long. I'll run 4 at a time. Okay, so now if we do box plots and pick the PMF ensemble, we should see that we've now got ensemble results for all the durations, which may give us a better indication of the PMP. If we wanted to change the way we select which temporal patterns adopted as representative for each critical temporal pattern, for example, if we wanted to use the maximum, we could change that here in the select adopted temporal pattern by, change that to maximum. You can now see it's picked the top. So not necessarily suggesting that's appropriate with PMP ensemble. I'm just saying you do have that flexibility to change how you're selecting your adopted temporal pattern. The final example I will show will include a climate change adjustment. I'll just copy that custom code in here. So that's this one's using the same temporal patterns here. But you can see here where we used to have a 0 for any rainfall adjustment. Now we have some climate change code. So it's saying here we want to use the temperature forecast for SSP2 4.5 for 2090 using median rates of change. And we're going to call it PMF ensemble climate change. And then if we hit create here, we'll get the same warning. I don't need to look at it again. But in these storms, you can now see, I think, yeah, rainfall depth adjustment here. So it's a 20% increase in rainfall being applied based on a 8%, based on a temperature change of 2.4 degrees and a rate of change of 8, which is in accordance with the climate change guidelines. So if we prepare and add that to the existing list, And then we run these new ones. And now we can we can compare them, for example. So they all have a 3-hour critical duration, but you can see how the single pattern compares to the Ensemble, quite similar, but then with climate change increase, it's quite a significant jump, as you'd expect with 20% extra rainfall. And look at that in hydrograph charts as well. Turn those on, we can see all 3 of these events. And here is the PMP normal with that rainfall adjustment. You can see that 20% extra rainfall has a large effect on the hydrograph, and also the time to peak reduces a bit as well. So I think that's all I needed to show you in Storm Injector, and I might just go back to the presentation quickly. Yes, so thanks very much for your time. It's yeah, really humbling to have over 100 people come and watch this, so thank you. If you have any inquiries for us, you can find us at software@csse.com.au, and there's a link to our website too if you're interested in trial software. Existing customers, if you just need access to the latest version, please let us know and we'll shoot it through. I'm happy to hang around for a little bit if there's any specific questions in the chat as well. But otherwise, thanks very much for your time. Let me just have a look if there's much written here. There's one question here: how can we scale pre-burst for climate change in Storm Injector? So if you use the pre-burst as a ratio of the burst and apply a climate change rainfall adjustment, then your pre-burst will increase as a proportion of that as well. What is the recommendation approach for PMP estimate and the temporal pattern between 6 and 24 hours? I don't think there is any formal advice, and I sort of don't propose to give any today, but as I said, we can interpolate rainfall depths and apply resample temporal patterns for the 12 hours and others between the 6 and 24 hours. Can you use the rainfall grid from CatchmentSIM in a rainfall on grid model? So the rainfall grid can be exported as a net depth, you know, and then I guess your rainfall on grid model may be able to distribute it over a temporal pattern. So I'd say yes. That was the questions. The chat. Okay. I know Shiraz has added some further links to other documentation, and also, yes, we'll be providing a recording as soon as I edit out my ums and ahs. And is there a way to apply the spatial pattern in Storm Injector? Well, that's what we're doing with the CatchmentSIM side of things. But if you have another tool like a GIS package or something that you might be doing spatially weighted rainfall depths, you need to create individual rainfall locations that you can apply to your sub areas in Storm Injector. That's how you can implement the spatial pattern in Storm Injector. All right, great. I think we will end it there, but we'll check the chat and get back to anybody that we didn't manage to get to